Let P of t and Q of t be continuous in the interval alpha beta, and let y1 and y2 be two solutions of star homogeneous, linear second order homogeneous. Then Wronskian of t is either always 0 or never 0 on the interval. It's either always 0 or never 0. So PQ quantity in this interval, and we have two solutions of homogeneous equation. Then the Wronskian is either 0 or never 0. So let's give a proof. First, we'll show that the Wronskian satisfies the first order differential equation. Okay, so we'll show that Wronskian satisfies this. How? We can just plug in. So I know that y1 is a solution. So let's say yi solution to star. So that is Ly of t equals to 0. That is yi double prime plus p of t yi prime plus q of t yi equals to 0 for each I equal to 1, 2. That's what we know. So what's Wronskian? Wronskian of t, which is Wronskian operator y1 y2t is y1 y2 prime minus y1 prime y2. So Wronskian prime, since each y is twice differentiable, it has y double prime, so Wronskian is differentiable one more time. So if we take the derivative, we get product. So it is y1 times y2 double prime plus y1 prime y2 prime. We did the product rule on this portion, and then we have minus, and then we're going to do the product rule there. So it is y1 prime y2 prime plus y1 double prime y2. That is equal to, these two cancels out. We get y1 y2 double prime minus y1 double prime y2. Okay, so let's plug this into this equation. W prime plus P of t times W, and we will see that that equals to 0. In other words, is this equal to minus P times W, y1 y2 prime minus y1 prime y2? That's the question. Okay, well, each yi double prime is from here, it is minus pt yi prime minus qyi from this star, right? So we'll plug this into here and there. So we get y1 times minus p y2 prime minus q y2. So that's yellow. And then we get minus p y1 prime minus q y1. This is yellow for y1, and then we get y2. That is this. Yeah. Okay, so let's see. Minus p y1 y2 prime, that is this, plus p y1 prime y2, that is this, and we get minus q y1 y2 plus q y1 y2, so that cancels out, so they are the same, so that is checked. So this is true. Then Wronskian T is either blank, then Wronskian T is blank. Hence, Wronskian T is 0 for all t or never 0 for all t. Wronskian satisfies this. So it satisfies a DE of the form y prime plus a of t y equal to 0. P is a function of t. So what's the solution? Y is either constant 0 or y is c e minus integral at dt, where c is not 0, right? So this tells me Wronskian solves, so Wronskian solves the dE y prime plus pt y equal to 0 on the interval alpha beta. This tells me Wronskian is a solution to this first order homogeneous differential equation defined in this interval. Hence, Wronskian is either constant 0 or Wronskian is equal to c minus integral pt dt, where c is not 0. So this solution is always 0. This solution is never 0. Therefore, this statement is true. Okay, so that's proved. So Wronskian is, we can say, 0 for all t on the interval alpha beta, or it is some constant e minus pt dt, where c is not 0. Okay. So it is either 0 or never 0. Note, this number 4 tells us that if Wronskian at some t0 is 0, then blank is, well, if I have two solutions, then number 4 said Wronskian of t is either 0 or never 0 on the interval alpha beta. So if it is 0 at some point, so it is alpha beta, Wronskian is either 0 everywhere or non-zero. So if it is 0 at some point t0, it should be 0 everywhere. That means Wronskian of t, when I compute for these two, Wronskian y1, y2, t is 0 for all t. Wronskian is 0 for some t0, for some t0 tells us that it is 0 everywhere. This means this set is not a fundamental solution. We said if Wronskian is not 0, then it is a fundamental solution, but Wronskian is 0, so they cannot be a fundamental set of solutions. So we fill in the blanks, then this is not fundamental set of solutions. So our question is, then when would Wronskian T be 0? So theorem, let PQ be continuous in the interval, PQ conti in the interval, and let y1, y2 be two solutions of star on the interval. So up to there is same condition as number 4. Then up to here we said Wronskian is either constant 0 or never 0. And if it is 0 at some point t0, then from number 5 we know that it is 0 everywhere in this interval. 0 for all t in alpha beta. So at the end we asked when Wronskian of t will be 0. Then, so this tells us the answer. One of these solutions is a constant multiple of the other. So either y1 is constant times y2 or y2 is constant times y1. Then, so if the Wronskian is 0 at some point, then one of the solution is a constant multiple of the other. So let's give a proof. By theorem 4, Wronskian is 0 for all t. Yeah. Case 1, one of the functions is constant 0 function on the interval. So we have y1, y2 solutions to dE. And that dE is homogeneous, so it is y double prime plus p of t y prime plus q of t y equals to 0. And we have two solutions. So case 1 is one of them is 0 on the interval alpha beta. We have two solutions y1, y2. So case 1, one of them is constant 0. Case 2, both are never 0. So that's case 1. Case 2, both are never 0. Never 0. They never cross the x-axis. Case number 3, either y1 or y2 is 0 at some point. So case number 3, in this interval alpha beta, one of the function hits the x-axis, the other I don't care. Okay, so these are all cases. Every different possibility belongs to one of these three cases. So let's do case number 1. One of the functions is constant 0 function on the interval. Because constant 0 function is a solution, right? It satisfies this D because it's a homogeneous D. So in that case, name the constant 0 solution as y1 and the remaining solution as y2. Then y1 is 0 times y2. y1 can be written like this because y1 is 0. It's a constant 0 function. So we achieved one of the functions, one of the solution is constant multiple of the other solution. So proof is done. Case 2, both are never zero function on the interval. Both are never zero. So y1, y2 are solutions, but they are never zero. And we also know that we are given that Wronskian t is zero, right? So that's y1, y2 prime minus y1 prime, y2. We know that this is zero on this interval alpha beta. Okay, so that tells us that y1, y2 prime is equal to y1 prime, y2. In other words, this is y1 prime y1 equal to y2 prime over y2. We can achieve this by dividing above equation by y1 times y2 because both are never zero. So we can do this. So that's what we get. We see that they are all functions of t. So we can integrate with respect to t. y1 prime y1 dt equal to integral y2 prime y2 dt. So this is ln absolute value y1 equal to ln absolute value y2 plus c. I'm gathering c here and c there together into this one c. And to combine these two, c is an arbitrary constant. So c can be anything. It can be 0, it can be a negative number, it can be a positive number. But I can write c, no matter where it is, I can write that as ln of something, ln of c1. Because ln is one-to-one function that covers all real numbers. So I can write this c as ln of c1, where c1 is some positive number. So the right-hand side is ln absolute y2 plus ln c1, which I can combine them as ln of c1 absolute y2. So I have ln absolute value y1 equal to ln c1 absolute value y2. So by exponentiating, I get absolute value y1 equal to c1 absolute value y2, where c1 is positive. Then I get y1 equal to plus or minus c1 y2. So by getting rid of the absolute values, I'm collecting plus and minus the signs here. Well, since y1 is continuous and y2 is continuous, c1 is nothing but positive constant, and y1 is never zero, never zero. Same thing here, these two are never zero. So on the interval alpha beta, it cannot be like this. So it cannot be plus and minus. It cannot take both signs at the same time. This means it is either kept as plus or kept as minus. So that tells us that on this interval, y1 is either kept as c1, y2 on the interval alpha beta, or y1 is minus c1 y2 alpha beta. It cannot be plus for some and minus for some. That doesn't happen because they are never zero. Okay, so anyway, I wrote one function as a constant multiple of the other. One function as a constant multiple of the other. So proof is done.